Hey everyone, and welcome to this explainer. Today, we are diving deep into what I like to call the hero's journey of digital bits. If you're an undergrad engineering student, especially if you're taking EEE 3207 Communication Theory, you are in exactly the right place. We're going to explore digital bandpass transmission techniques. Basically, we're looking at the math and the physical reality of how we take incredibly fragile digital data and forge the absolute best armor for it, so it can survive the wild, noisy, unpredictable journey through real-world communication channels. It's a fascinating topic, so let's get right into it.
Here is our roadmap for today. First, we'll look at baseband versus bandpass transmission. Then, we'll break down the core modulation techniques. Third, we'll tackle channel noise and how the receiver handles it. After that, we'll level up to advanced modulations and M-ary systems. And finally, we'll wrap up by visualizing constellations and comparing overall system performance.
All right, part 1, baseband versus bandpass transmission. Let's set the stage. So why do our bits even need to leave baseband in the first place? Well, baseband transmission is kind of like sending a signal down a very safe, simple wire, a low-pass channel, using discrete pulse amplitude modulation. And in that cozy environment, the main enemy you're battling is intersymbol interference, or ISI, where your pulses basically smear into one another. But in the real world, we usually need to transmit over the airwaves or through massively complex networks. That requires bandpass transmission. Suddenly, we have to modulate our data onto a high-frequency sinusoidal carrier. And the moment we do that, the primary enemy completely changes. We aren't just fighting ISI anymore, we are in an all-out war to minimize symbol errors caused by unpredictable channel noise.
Now check out how we actually construct this bandpass signal to protect our data. We use a really elegant mathematical approach called complex envelope representation. Look at the architecture here. Our message source goes into a signal encoder, which splits it down two distinct low-pass paths. You've got your in-phase component, that's the GI of T, and your quadrature component, the GQ of T. These two components modulate two orthogonal carriers, literally just a cosine wave and a sine wave perfectly 90 degrees out of phase with each other. When you sum them together, boom, you get your bandpass signal. Blending these in-phase and quadrature components is the secret sauce. It's the foundational armor for our data.
Moving right along to part 2, the core modulation techniques.
To actually transmit binary data over these bandpass channels, we need to modulate that sinusoidal carrier wave we just built. We do this through keying, which is really just a fancy word for switching a specific property of the carrier wave based on whether we're sending a 1 or a 0. We've got 3 basic flavors: Amplitude-Shift Keying, or ASK, where we switch the amplitude; Frequency-Shift Keying, FSK, where we switch the frequency; and Phase-Shift Keying, PSK, where, you guessed it, we shift the phase. Now look closely at this comparison. FSK and PSK have a massive, massive advantage. They feature constant envelopes. Because their overall amplitude never fluctuates, they are practically weatherproof against the kind of unpredictable channel nonlinearities that would totally wreck an ASK signal.
When you see it visually, it instantly clicks. In that top waveform, ASK, the carrier amplitude is literally just flicked on for a binary 1 and off for a binary 0. Super simple, but kind of fragile. In the middle with FSK, the amplitude stays perfectly flat, but look at the frequency spacing. It bunches up tightly for one binary state and stretches way out for the other. And down at the bottom with PSK, both the amplitude and the frequency are locked in completely constant, but the wave's phase abruptly flips, usually by 180 degrees, the exact moment the data switches between a 1 and a 0.
So, how do we forge this PSK armor from scratch? Let's take binary PSK, or BPSK, as our prime example. It's just a logical 3-step process. Step 1, you grab your raw binary data, just a plain old sequence of 1s and 0s. Step 2, you map that data into a bipolar line code. Basically, you're translating discrete digital logic into actual positive and negative voltage levels. And step 3, you multiply that bipolar signal directly with your carrier wave to generate the final transmission-ready BPSK waveform.
Let's look at those steps in action. The top row is our raw data sequence. Right below it, you see the bipolar line code. Notice how a binary 1 is just a positive voltage block, and a 0 is a negative voltage block. When we apply step 3, we get the bottom sequence, the actual BPSK waveform. See how the 180-degree phase shift lines up flawlessly with the transitions in the bipolar code? In BPSK, we are dealing with two signals that are entirely antipodal. They are exact mathematical opposites, which gives the receiver the absolute maximum contrast to tell a 1 from a 0.
Which brings us to part 3, channel noise and signal reception.
All right, this is where the real world hits hard.
On the left side here, our beautiful, pristine bandpass signal enters the channel. Almost instantly, it's attenuated, and worse, it gets attacked by additive white Gaussian noise, or AWGN. So what actually arrives at the receiver is this messy, degraded combination of a weakened signal and totally random noise. But don't worry, our heroic receiver is ready. First, it uses a bandpass filter to chop off all the excess noise outside our specific frequency band. Then it uses an incredibly precise IQ down converter, firing up local sine and cosine oscillators to split that messy signal right back into its in-phase and quadrature low-pass components, desperately trying to pull the original message out of the wreckage.
To actually recover those exact ones and zeros, the receiver uses a really powerful trick called coherent detection. If you look at these block diagrams, you'll spot a multiplier followed by an integral sign from 0 to t sub b. T sub b is the duration of exactly 1 bit. The receiver literally integrates the incoming signal over that precise time frame. By doing this, it mathematically yanks the persistent signal energy right out of the fluctuating random noise. It spits out a single value. Then, a decision device just looks at that value and says, hey, is this greater than 0? If yes, it's a 1. If not, it's a 0. It's elegant, and it works brilliantly.
Let's keep moving. Part 4, Advanced Modulations and M-ary Systems. Okay, before we start packing way more data into these signals, we have to clear up a massive conceptual hurdle, the difference between bit rate and baud rate. Bit rate is easy, it's just how many raw bits of information we push through per second. But baud rate, that's the speed of the actual symbol changes on the wire per second. Now in basic BPSK, one symbol represents 1 bit, so bit rate and baud rate are the exact same number. But in advanced M-ary systems, a single symbol can carry multiple bits. When you do that, your baud rate, the physical speed of the modulation, is actually lower than your data bit rate. Keep that in mind, it's a huge distinction.
Now here's a really clever engineering workaround, differential phase shift keying, or DPSK. Remember coherent receivers? They are super precise, but they require the hardware to perfectly lock on to the exact absolute phase of the incoming carrier wave. That is notoriously difficult and expensive to do. DPSK just entirely sidesteps the problem. Instead of caring about the absolute phase, it encodes the data in the phase transitions between successive bits. The receiver just compares the current signal with a delayed version of the previous bit. If the phase stayed the same, it outputs one thing. If it flipped 180 degrees, it outputs the other. It's a fantastic shortcut that saves a lot of headache.
Let's look at a true M-ary system to see how we level up our capacity. Enter quadrature PSK, or QPSK. Here we are literally doubling our spectral efficiency. How? By packing exactly 2 bits into every single transmitted symbol. 2 bits gives us 4 possible combinations, right? 00, 01, 10, and 11. So we transmit 4 distinct phase values. You can see the math on the left, but visually on the right, it's beautiful. It maps perfectly to 4 corners of a 2D spatial grid. With just a single pulse of our carrier wave, we're delivering twice the information as BPSK.
Finally, let's wrap up with Part 5, Constellations and System Performance.
I love this part. We can actually visualize these digital transmission systems as constellations, hovering in a geometric signal space. Every dot on these grids is a unique digital symbol plotted on an IQ coordinate system, in phase on the horizontal, quadrature on the vertical. Look at diagram A. Simple binary ASK and PSK just sit right there on a flat 1D line. But as we upgrade to M-ary systems, the whole space opens up. You see the 4-point QPSK circle, the 8 PSK circle, and then look at diagram D. That's 16 QAM. That's a massive 2D grid where we are modulating both amplitude and phase at the same time to create 16 distinct targets. We are packing 4 bits into every single dot on that grid.
But there's no free lunch in engineering. Denser constellations come with serious risk, and this bit error rate chart is the ultimate scoreboard. The horizontal axis is basically our signal-to-noise ratio, our signal energy fighting against the channel noise. The vertical axis is the bit error rate. How often does a bit get accidentally flipped by the noise? Now, the lower the curve on this graph, the higher the survival rate. Look at how amazingly coherent binary PSK and QPSK perform compared to the non-coherent systems. This graph is absolute mathematical proof that maintaining phase coherence gives your bits the toughest possible armor against that additive white Gaussian noise.
And here is your ultimate cheat sheet. This table distills the exact mathematical probability of error for every modulation scheme we've talked about.
Notice that the absolute top-tier performers, coherent PSK, FSK, and QPSK, all rely on the Q function. That function dictates a really steep, strict drop-off in errors as you pump up the signal energy. On the flip side, the non-coherent systems rely on an exponential function. They don't perform quite as flawlessly, but remember, the trade-off is that their receiver hardware is way simpler and cheaper to build. As an engineer, this table lets you calculate the exact survival odds of your data based on the armor you choose.
Which brings us to the real bleeding edge of communication theory today. We are constantly demanding faster and faster networks, which means moving from 16 QAM to 64 QAM to 256 QAM and beyond. We are packing those constellation dots closer and closer together on the grid. So I want to leave you with this question. Knowing what you now know about additive white Gaussian noise, how densely can we realistically crowd these constellations before the unavoidable channel noise just blurs all the points together, completely swallowing our data? It is the ultimate engineering balancing act, and honestly, it's a problem your generation of engineers is going to have to solve. Thank you so much for joining me on this explainer to explore the hero's journey of digital bits. Until next time, keep exploring and keep building.